Okay, so here we are going to talk about the proximal gradient methods. So this would be a extension of the gradient method. And this proximal part is the key of this method. Basically, now we are going to see that in machine learning and signal processing, and also in statistics, there are many optimization problems that involve both differentiable and non-differentiable terms. And we will need this proximal method to handle those non-differentiable terms. Okay. So the proximal gradient algorithm is developed for solving composite, for minimizing composite functions, where we have where the function involves multiple terms. In the previous lectures, we were talking about minimization of fx. There's only one term in the objective function. But in many applications, depending on the specific formulation, the objective function may involve multiple terms. So the structure will be highly complex. So we will first talk about this so-called composite function or composite optimization problem. The formulation is simply a generalization of the previous one. The objective function now involves two terms. Fx is what we talked about in the previous lectures. It is basically the loss function. For example, it can be the classification loss in binary classification, or the mean square loss in the least mean square problem. But this hx is new. This hx function is what we usually call the regularizer. So we impose this function to regularize the problem, to penalize the problem solution in a certain form. For example, if we want to constrain the parameter x, then we can design hx as the indicator function on the constraint set. We will talk about this later. And there are many other applications where we want to restrict x on the subset of solutions that has certain implicit structures. For example, sparsity is one of the most important structures in the modern statistics and machine learning. Okay. So in this problem, here we are talking about general problem formulation. Well, fx is convex, differentiable, and smooth. For example, it could be a quadratic function or it could be a least mean square loss that we have seen before. And the hx is a convex regularizer which may not be differentiable. For example, as we will see later, this could be the L1 norm of x. So L1 norm is convex and it's not differentiable. Okay. So this problem is called composite optimization problem because it involves two terms, and then it is complicated because it is partially differentiable. Now this term is differentiable, nice, very, very nice. And the regularization term usually is very simple but non-differentiable. Okay. And you see, for this problem, we do not have any constraint because the constraint can be encoded into the function h. And we will see how to do this later by introducing the indicator function. So some very important examples that we will see in the homework problems is the L1 regularized minimization problem. Okay. So we're going to minimize fx. Well, this fx describes your problem It's like data fitting error. For example, in the least mean square, we are trying to fit a linear model into the observations. So this part is the standard part from your underlying application, and we add this L1 norm to penalize the L1 norm of the solution. So intuitively, once you add this norm as a regularizer, and then when we minimize this function fx, we will have to consider the L1 norm of x. We want to make sure that we find a solution that minimizes fx and also sort of minimizes the L1 norm of this function, right? So this is called penalty or regularization. So usually we will add a lambda in front of the L1 norm just to balance these two terms based on different applications. But this term is equivalent to the following one. Okay, so sometimes we will write this the first row is the regularized form. Well, we regularize our objective function fx by adding this regularization term lambda times x, lambda times the L1 norm of x. Right? And by adding that, when we minimize fx, we have to pay attention to the L1 norm of the solution. Let's say if you find a very good solution x that can achieve a very low value of fx, however, that solution has a very high L1 norm, then that is not the desired solution for this problem. Okay. So we are introducing this regularization term to filter out those solutions whose L1 norm are too big. So this problem can be equivalently understood as the following constraint form. Well, basically, we are minimizing this objective function. Okay, now I'm going to write this regularization as into a constraint, subject to the constraint that the L1 norm of x is less than or equal to some positive number. Okay. So these two they are connected through the duality, but intuitively you can sort of see. In the first problem, we are penalizing the L1 norm, and whereas in the second problem, we are constraining the L1 norm. So they are kind of doing the same thing. And you can replace this L1 norm by any other regularization you want to use. But L1 norm is a very important regularization that we use to impose sparsity. Sparsity. Okay, so what is sparsity? Sparsity basically is defined as the number of non-zero entries of x, okay, which means so sparsity means that your solution x must be sparse. Only a few entries of x can be non-zero. Okay. And this structure turns out to be very important and very frequently appear in many problems. For example, if we consider images or many typical signals, they are sparse under a certain representation. Yes. For some images, if you take Fourier transform, they may have a sparse representation. But for images, we have some standard wavelets basis where we can represent images efficiently using sparse representation. So you can view sparsity as kind of information compression. Well, there's a lot of redundancy in many of the signals that we see in the daily life, and if we find a proper solution, a proper model for those signals, we may end up with a very sparse representation. So this is a very important topic, and we will see many applications in the homework. So the number of non-zero entries of X, this definition is actually corresponding to the L0 norm of X. The L0 norm, which is not a norm technically speaking, but the L0 norm is following the same definition as the LP norm, where you set that P to be 0. And once you do that, it reduces to this definition. So L0 norm of X simply counts the number of non-zero entries of X. Right. So you have a vector X, you just look at how many entries are non-zero. Okay, count that number. And this L0 norm, so why do we use L1 instead of L0 norm? Well, there are lots of reasons. And one of the important reasons that L0 is not convex. It's non-convex. So solving this L0 problem is an NP-hard problem. Okay, there's no polynomial algorithms to solve that. So it's very hard. And the other thing is that sometimes it is too extreme. It is too discrete. Like it only counts the strictly all the non-zero entries in the vector X. So for example, if you have a vector, well, every entry, well, there's a lot of entries that have very small magnitudes. Okay, imagine this. You have a very high dimensional vector with many entries with very small magnitudes. Now, technically speaking, according to this definition, if you count L0 norm, every single entry will add 1 to this L0 norm, right? But on the other hand, you feel like this is a bit unfair because these entries are almost 0. But so maybe it's just fine to ignore them. So that's why we introduce in practice, people can show that this is a very good approximation of the L0 norm, and it's very nice because it's convex. L1 norm is convex, and also it is not that it is a continuous function, so that for this vector, if you evaluate this L1 norm, still you get very small number. So it is a sort of avoiding those that extreme case that we see in the L0 norm. So it is a very good approximation of L0 norm. In fact, we can show that this is the best convex approximation for this L0 norm. So that's why people use L1 norm instead to impose sparsity. So we put this, when we add this L1 norm to Fx, we are looking for a solution that minimizes Fx and at the same time is sparse. We are looking for a sparse solution. Now, the other example that we will see in one of the homeworks later on is the nuclear norm regularization. Well, this is a matrix valued function, Fx. capital X is a matrix. And we are adding the nuclear norm of the matrix as a regularizer. Well, so the nuclear norm, recall the definition, is the L1 norm of the singular vector of this matrix. So you take all the singular values of this matrix, compute their L1 norm. And because of the definition, basically we are looking for a solution, a matrix solution X that has sparse singular values. Okay, because right, this nuclear norm is L1 norm of the singular vector. So sigma X denotes the vector formed by all the singular values of this matrix. For this vector, we compute this L1 norm. Okay. Now, if we put this as a regularizer, that means we are looking for a matrix X whose singular values are sparse. Only a few singular values are non-zero. So this means, essentially, this means we are looking for a low rank matrix X. Low rank matrix. Now in the extreme case, right, if a large matrix has rank 1, that means all the columns and the rows are linearly dependent. So basically, they look pretty much similar to each other. And we will use this technique to do a video, like moving object detection application in one of the homework problems. Okay. Because now, so we can quickly look at this idea. Moving object in a video. We can model this as a low rank matrix separation problem. So where does the low rankness come from? Now, we can consider 3 consecutive frames where we have a moving object from left to right. Okay. Now, how do we model this problem? You see that there's a static background plus a moving object, right? So we can, for example, we can stack each frame into a column vector. Okay. This is a matrix. Now I stack it. I put all the columns one by one. I stack it column-wise. It becomes a very long column vector. Okay. By doing that, this moving object, right? Its pixels will be somewhere around this column vector. Like for example, it could be here. Right? And I do this for this one. But since this ball has moved, maybe it is here right now. And in this one, maybe it approaches the bottom part of this column vector, right? And once you stack these columns together, right? Imagine you will have hundreds of frames. Well, you have a static background and a moving object. Now, if you stack all those column vectors together, it becomes a low rank matrix plus some moving objects. Right. So if we stack these columns together, it becomes, you can imagine there's a static background where there's no moving objects, just the static background plus some noise. Right? So this is your data that you have a video sequence, right? With moving objects in it. This is original data. And following this idea, we can model this problem as how to separate this this video sequence into a static background plus some noise. And these two parts have very different structures. For the static background part, because it is a static background, so basically every column is exactly the same with each other. So this is a rank 1 matrix. This is a low rank matrix. Right? Because every single column corresponds to that static frame, the background. So they are the same. So that gives a, in fact, it is a rank 1 matrix, but you can say it is a low rank matrix. And the moving objects are basically some random pixels, randomly moving around these columns. So this can be modeled as a noise, So the problem is that given such a video sequence, so we can view this video sequence as a mixture of a low rank matrix plus noise. And then we are going to do an inverse problem where we are given this mixture matrix. Can we find an algorithm to separate these two parts, a low rank part plus a noise part?
What does it mean to be low rank?
Well, yeah. So in this case, right, every column, all the columns are exactly the same in this static background, right? So imagine now now this matrix, you have a matrix where all the columns are exactly the same. This is a rank 1 matrix, right? Because all the columns are the same as each. They are not just the same size, they are exactly the same. Because, right, remember, every column is basically a stack of the, it's a column stacking all the columns of these frames.
Oh,
right?
I see. They're the same because it's the background.
It's the background, right? So we assume that there's a static background and there's a plus a moving object. Right. So if you only stack the background part together, all the columns, right, all the frames of the backgrounds, they are the same. So these columns are the same. And on the other hand, the moving objects, you can sort of understood it as a kind of noise randomly distributed along these columns, right? So this makes this problem very interesting. Given a mixture of a low rank plus okay, so this part is a low rank matrix. Now what about this part? The moving object, if we assume the object is relatively small and it's moving around randomly, so this part is sparse. It's sparse. A very sparse matrix corresponds to that small moving object. Okay. Now the question is, given a mixture of a low rank plus sparse matrix, because the video is basically a moving object moving around in the static background. Given such a mixture, is there any hope to separate these two parts perfectly? Okay. And this can be done by such a model, by adding nuclear norm and L1 norm, by putting them together to model this signal separation problem. And later on, we will talk about how to model that and how to design algorithms to solve this problem. It's a very, very interesting problem. Okay, so this nuclear norm is also very you can view it as a matrix version of the L1 norm, where it's basically the L1 norm of the singular values. Okay, so we put this norm to promote a low rank solution. Low rank solution. And for in this lecture, we are going to design algorithms to solve these problems. And we start from the gradient descent, okay, because we are familiar with this classic algorithm. Now, gradient descent is in the previous lectures where we focus on this simpler problem, right? Minimize a single objective function fx, and the fx is differentiable, it's smooth and convex. Very nice structure. So we can do this gradient descent method. Okay, this is the update rule. And in the previous lecture, we have shown that gradient descent has the following equivalent update rule. So this update rule can be rewritten as a solution to this quadratic minimization problem. Right? Simply take the gradient of this part, set it to 0. It exactly gives the gradient descent update. So this is a first order Taylor approximation at the current point xt, and we have plus this residual term, right? And in the mirror descent algorithm, we further talk about how to generalize this Euclidean term to other divergence. But here we will just focus on the standard gradient descent. Okay. So this is a first order approximation plus the proximal term. So together, this builds a local quadratic approximation of the objective function. And then we are looking for a minimization to this simpler problem. And these are the illustrations that we have talked about before. So I will skip this. And then in the follow-up lecture, we also talk about projected gradient descent, right? Where where the problem becomes a constrained version, the minimized fx subject to a convex constraint. And the algorithm is very straightforward. We do a gradient descent, and then we project the updated variable onto the convex constraint C. And then this update rule, and we have also shown this previously, this update rule can be rewritten into the following form. Well, it's basically these terms are from the gradient descent update rule. And the only difference is that we add an additional indicator function as a regularization term. Well, this indicator function is defined in this way. If x is in the constraint, then it is 0. So it doesn't change the problem. Otherwise, it is, if x is outside the constraint, it becomes infinity, which makes the problem meaningless, right? So intuitively, you can say that by adding this indicator function of x, we are essentially restricting the optimization of this part within the constraint set C. Because whenever x is in the constraint, it is 0, doesn't affect this problem. Otherwise, it becomes infinity, makes the problem meaningless. So the only meaningful part of this problem is when we restrict x within the set C. And we can show that this one can be by completing this square term is equivalent to the following one. And this is exactly the projection operator that we write here. Okay. Think about that. This is the we are looking for. So basically, this part will basically restricts our x within set C because it's an indicator function. It only makes the problem meaningful when x belongs to the constraint set C. So we can absorb this term into a constraint set. They are equivalent. Right. So basically, this is a simple trick. When we say minimize fx for x belongs to C, we can also say that we can add an indicator function and then get rid of this constraint. Okay. Previously it's constraint version, but now it's unconstrained version by introducing this indicator function. Because indicator function, what it does, if x is in C, is 0, doesn't affect this objective function, right? So as long as x is within the constraint, we are basically looking at the above this problem. If x violates the constraint, well, this becomes infinity, makes the problem meaningless. So we don't really need to consider that case, right? So it is essentially equivalent to say that we are minimizing fx within the constraint set. Okay, so this is a simple trick. So that's why we have this indicator function here. Basically, you can instead of putting it here, you can also move it to the constraint set. So the argmin will be over the constraint set C. Okay. And similarly for the second line, you can move this part into a constraint, to the constraint part. Right. Now, if we do that, then this is basically projecting this point onto the constraint set C. Right, because we are looking for x that has the minimum distance to this point, while x is restricted within set C. And that is exactly this projected gradient descent update. We are projecting this point onto the set C. Okay. So you see that for projected gradient descent, we have such a equivalent form of this algorithm. Now let's put these things together. Okay, if we do minimize fx, we have from the previous. This is the previous update. So I will, to simplify, I will just ignore the contents. Okay. This is a gradient descent following these terms. And now in the projected gradient descent, we are looking at this problem. So here, right, I rewrite the constraint optimization problem into a regularized form, right, by introducing this indicator function on the set C right? I can get rid of the constraint. So it is like a regularized problem. Well, the regularization term, this indicator function is the regularization term that restricts our solution within set C. Right? And the projective gradient descent update rule is all these three terms plus that indicator function, right? So as we have seen in this line, it's all these three terms plus this indicator, plus this regularization term. And from these two lines, these two algorithms, we can sort of tell the philosophy of designing these optimization algorithms. In gradient descent, because fx is very nice, it's a convex smooth problem, so we can have a very accurate local approximation of this problem. So we build a local quadratic approximation of this problem and we solve it one by one, right? But in the constraint optimization problem now, we can understand it as a regularized form. Well, we are regularizing the objective function using this indicator function. But this indicator function, because of this form, it has a sharp, like on the boundary of this constraint C, it immediately jumps from 0 to infinity. So it is a highly non-smooth function, but it is convex, but it's non-differentiable. Okay. So for the constraint problem, we start to see some complex structures induced by this regularization term. So how do we do it? How do we handle this problem in the projective gradient descent? Well, according to this algorithm design, we will treat these two parts separately. I still want to build a very nice approximation of this problem in every iteration. So what I do is, because fx is very nice, very smooth and differentiable, so I can just reuse this local approximation of this function. But for the regularization part, it is not differentiable. It's very hard to approximate it. So I will just leave it there. I will just leave this regularization function to my approximation model. Okay. So the approximation model now becomes a local quadratic approximation for the fx part plus the regularization part. And then it turns out that if we simplify these lines, it can be, now this regularization part can be reduced to a projection operator, right? So that is also doable if the projection is relatively simple for many constraint sets, right? So you see, the philosophy is that we keep this part untouched, keep this non-smooth part untouched, and only breaks down the smooth part, only breaks fx into a local quadratic part. So once we go to this more general formulation of composite optimization problem, right? Well, this regularizer is not necessarily the indicator function. Could be any other arbitrary convex regularizers may not be differentiable. For this problem, the idea will be very similar. We just, for this part, we use that local quadratic Taylor approximation, and then we will leave this part untouched. And the algorithm we designed is basically based on such a approximation model. And this motivates us to introduce this proximal operator. Okay, because in this problem we are looking for we are solving a minimization problem. Well, this part is quadratic plus the regularization part, right? And this we can view this as an operator. So this motivates us to define this abstract proximal operator. And here's the definition. So this operator is associated with a function h, which is the regularization that we talked about. So what this operator will map any arbitrary point x into another point via the following optimization problem. Okay. So this operator will map x to the minimizer of this optimization problem. So this is what this operator does. Maps x to the minimizer of this quadratic optimization problem regularized by h function. Okay. Now let's look at this optimization problem. Now x is given. X is the input of this operator. So this x is here. Right? And we are looking for a z that minimizes the distance to x plus hz. Right? So this is like a strongly convex optimization problem. Because so this optimization problem is over z, but x is given and we are doing optimization over z. And then this part is strongly convex in z because it's a quadratic distance, Euclidean distance. And hz, we assume it is a convex function. So a convex plus strongly convex. So the entire problem is a strongly convex optimization problem. So this is the definition of this operator. Takes x as the input and maps this point to the minimizer of this optimization problem. Now, according to this definition, we can write projected gradient descent in the following form. Okay. Yeah. So this is a projected gradient descent. So let me copy it here. So it's arc mean x and the plus the indicator function. Okay, this is a projected gradient descent. Now we compare this update rule with the definition of the proximal operator. You can see this part is the hz part. Right? So here we are using we are using x instead of z. Okay, but so this is that part, And this point, the point we are considering is this point. So this is our x is our z, and this is our x. So this is our h, no, hz, right? This is our z. This is that x, right? And then you see this falls into that definition of proximal operator. So we can express this projected gradient descent update in the form. It's basically the proximal operator associated with this indicator function, eta times indicator function is what is our h. Is the proximal operator associated with this regularizer evaluated at this point, and this is that point to be evaluated. Okay. So in this sense, we can conclude that this proximal operator of the indicator function is basically the projection onto C. Okay, so the projection operator can be viewed as a special case of the proximal operator. Is the proximal operator associated with the indicator function on the constraint set C. So in this way, we're kind of putting constraints, treating constraints as a kind of function. If you have a constraint set C, it can be equivalently mapped into an indicator function on that constraint set. And then the projection onto this set is simply the proximal operator associated with the corresponding indicator function. So this shows that the proximal operator is a very, very good generalization of the projection operator. Okay. When we talk about projections, we always talk about sets, constraint sets. But now when we introduce proximal operators, we can define it for every single function h. And then the algorithm for solving that composite optimization problem is simply proximal gradient descent. Okay, so let's go to the problem. This is the composite optimization problem. We first do a gradient descent. This is the same part. For the nice differentiable part, we do a gradient descent. Okay? And then how do we handle this possibly non-differentiable part? We further map it under this proximal operator associated with this function eta times this function h. Okay. So it is sort of like a generalization of the projected gradient method, but now the projection is replaced by a more general proximal operation for functions. See if we have yeah, maybe I can write this more explicitly. So the problem we are talking about is this one. Okay, and then remember, based on that, following that logic, the way we design this algorithm is that every time I build, I want to build an approximation model of this composite problem, right? And I know F part is nice, differentiable, convex, so it can be locally approximated by that Taylor expansion. Okay, so let's go back to this, go back to this model. So it's fxt plus gradient fxt x minus xt plus 1/2 eta t x minus xt square. And okay, so this is the local approximation for the F part, right? And then for the H part, it can be very complicated. It can be non-differentiable. So we will just leave it there. Okay, the idea is just leave it there. So the approximation that we build is simply a local approximation of F plus Hx. And this is our algorithm. This is our algorithm. Okay, and you can show that by simple algebra, you can just rearrange things, complete that square. You can show that this is equivalent to the following. Right? These are constants. So what you do is to get something like this. It's 1/2. You complete this big square terms. X minus xt minus eta t plus eta t hx. Okay, you can show that these two are equivalent. You can multiply everything by eta t so that you can have that. Multiply everything by eta t, so you have this eta t in front of h. And then for the rest of the terms, you complete that square term. It will become this. It will become this term. Okay, and this by definition, look at this part. Inside this point is the gradient descent step, right? And if you view it as a single point, then look at this optimization problem. It's 1/2 x minus something to the power of 2 plus another function. This is exactly falls into this proximal operator definition. Right? It's 1/2 quadratic distance plus this regularization term. Okay, so this part is exactly proximal operator. Now look, this is how we write this notation. You have to. This is the original definition, so you have to follow this one. The H is right. It's in the subscript of this proximal operator. It's H. Okay. And in our case, H is eta, a constant times H, eta t times H. So this is our function. Our function is eta t times H. Okay. Right here in the definition is H, and then H in the subscript. So here we have eta t. And where is the point? Here we are evaluating at x. X is inside this quadratic term. So in this case, this is our x. This is that constant input. This is that input to this operator. So this would be xt minus eta t. t. So this is the proximal gradient descent, because it is a proximal step composite with a gradient descent step. Right, so this is the this proximal gradient descent algorithm. And this framework generalizes that projective gradient descent. To recover projective gradient descent, you simply set hx to be the indicator function of a constraint set. Right? Let's say if hx is an indicator function on a constraint set. Right? If you do that, the problem now, if this is that indicator function, then the problem is a constraint optimization problem because of the indicator function. And consequently, this part, this operator, this proximal operator, and this is the now the h becomes the indicator function, right? So we have eta t is a proximal operator associated with eta t times the indicator function. This guy is the projection onto C. This is projection onto C. So this algorithm reduces to projected gradient descent. And we can see this by following the definition. If h is an indicator function, think about that. The indicator function we can basically put it back into a constraint. So we are looking for a z that has the closest distance to x, while z is restricted within C. Right? This is exactly the projection operator, the definition of the projection operator. Right? So this proximal gradient algorithm is a more general framework to handle these composite optimization problems. And this covers the constraint optimization as a special case. So the algorithm, proximal gradient algorithm, covers the projected gradient descent as a special case. Okay. And this algorithm is actually, by its form, it's very simple. It's basically first you do a gradient descent update, you get that point. And then you just need to figure out how to do that proximal operation, right? How to implement this operator. It is just like in the projected gradient descent, we had to figure out how to do that projection. Right? If the projection is complex, then the problem may be hard to solve. But we do see many examples where the projection can be done analytically. So this algorithm, of course, it will be useful if that operator can be implemented in an inexpensive way. So I guess the next question is how do we compute this operator, right? How do we implement this operator, given some examples of H? So this is our next part. We will focus on that proximal operator and see how to compute, how to analytically compute this operator for some important examples of H. So it turns out, as we will see very soon, this operator can be efficiently evaluated for many widely used functions, in particular regularization functions. And we have seen this. If H is the indicator function, if H is the indicator function of a convex set, so specifically H takes this form. Okay. And this is an illustration of this H function. Let's say if this in one dimension, if the constraint C is an interval, right? Then within this interval is 0, and outside that you go to infinity. So that's like a non-differentiable, non-smooth function. And in this case, the proximal operator, as we have seen, becomes this one. Because by definition, so we first write out the definition of proximal operator. And we are doing our argmin over Z. Okay. And because this is the indicator on C, so it is equivalent to argmin. Well, now I'm restricting my Z onto C. And then I can just consider this term only. Because H is the indicator. And then, okay, minimizing the distance square is equivalent to minimizing the distance. It doesn't matter. And also we can ignore the coefficient 1 over 2. Doesn't affect the minimizer. So in the end, it is equivalent to this one, right? Because on the right-hand side, we are talking about the minimizer, not the problem, the minimizer of the problem, right? Here, based on this definition, we are looking for the minimizer is the closest point to X within set C, right? Because it is a distance to the power of 2. And here is the same thing. We can ignore the power of 2 and also ignore the 1 over 2 because they do not change the minimizer. It is always the projection of X onto C. Okay. So this is a very simple example. Very simple example. When H is indicator function, proximal operator is projection. A very nice generalization of the projection operator. Okay, the second one is L1 norm, a very important, very important example. If H is lambda times L1 norm, okay, because this is how we introduce this L1 norm minimization, right? We add lambda times L1 norm to the objective function. Well, lambda, you can choose a coefficient that balances these two terms. But if you choose a very large lambda, maybe you are penalizing the L1 norm heavily. If you choose a small lambda, okay, the weight is become less important. So this lambda is something that you will pick. Okay. But in this problem, right, this H is lambda times L1 norm. Okay, now how do we compute the proximal operator of this problem? And it turns out this operator has a very interesting closed form solution. Here's how we do this operator. If you give me an X, I think here should be H instead of lambda H because lambda is already defined in H. So I think this should be a typo. So let me make things clear here. So H is this one. Then we are looking at this one. Looking at proximal operator of H. Okay. So specifically it's lambda times L1 norm. Yeah. Okay. The proximal operator associated with this function, lambda times L1 norm. This operator will map every point in this way. So this is the definition. If you look at definitions, this is an entry-wise operator. So for every entry of X, so let me see. There is a if X is bigger than lambda, okay, here's entry-wise, okay, because X is a vector. So for every entry, you look at this relation. If that entry is bigger than lambda, then you subtract lambda. You subtract that entry by lambda. Otherwise, if X is less than small negative lambda, then you add lambda. Okay. Now, if X is between lambda, these are complementary cases. If X is between, then you just put 0. Okay. So in MATLAB, you can do this in parallel. It's simply because this is applies entry-wise. So I think this can be done in a compact form. Let me see. Yeah, so I think there's a simpler way to write all these 3 different cases into one analytical form, but I need to check that. But this is a very simple mapping, right? And intuitively, so it is called soft thresholding. Because the function looks like this. Right? If X is between lambda and negative lambda, then you output 0. So that corresponds to a flat horizontal line. Okay. If X is bigger than lambda, what is the mapping is X minus lambda. So it's like a line shifted to the right by lambda, right? So that's this line segment. If X is less than negative lambda, you have X plus lambda. So that's this one. So this is called soft thresholding. First of all, it is a thresholding operator because the last line is a filter. If it detects that for certain entries, the magnitude is less than lambda, it will filter them out, right? That's why this L1 norm promotes sparsity. Right? Because when you add that L1 norm and do proximal gradient descent, that proximal that proximal operator has this thresholding effect. So for those entries with small magnitudes, it will remove those entries. So the solution will be sparse, right? That fits our intuition. And for the other entries where the magnitude is bigger than lambda, it will simply shift them by lambda. So it's like reducing the magnitudes by lambda. So this is a soft thresholding operator. And you can see from this graph, it is soft because it is continuous and Lipschitz. So it's mathematically speaking, it is a very nice mapping. It's a very continuous mapping, and the Lipschitz continuous. Okay. So that's why when we introduce this L1 norm as a regularizer, we are promoting sparsity to the solution. Okay, and the question is, how do we get that? How do we derive this analytical form? Well, we simply follow the definition of L1 norm. Let's look at this definition. By definition, in this arc, the minimizer arc mean z, well, z minus x squared plus lambda z L1 norm. Okay. And this problem seems complicated because it has that nice differentiable term plus a non-differentiable L1 term. But this problem has a very interesting structure because both two terms are separable with regard to the dimensions. So I can rewrite it as, now distance to the power of 2 is basically the entry-wise distance. Right? Entry-wise raise it to the power of 2 and take summation. This is the L2 square. And the L1 norm by definition is lambda. Again, by definition is entry-wise summation of the absolute value. Right. And you can see all the dimensions are perfectly separated. So we can simply perform this minimization for every dimension. So for every dimension, so this is like the so we can focus on each dimension zi separately. And for every dimension, I'm going to we simply need to look at this one-dimensional optimization problem. But this is a one-dimensional problem over the ith dimension, and well, I can be from 1 to d. And this is a one-dimensional problem, right? So you can solve this analytically, and you can get this soft thresholding operator. Okay. You just need to divide it by 3 cases. You assume zi is bigger than 0, and then zi is bigger than 0, zi is less than 0, and zi is equals to 0. And then you can solve this quadratic equation and get the minimizer. Okay, so this is only a one-dimensional problem. And for every dimension, the solution turns out to be such a soft thresholding operator. So in the end, you concatenate all the solutions together. And so this can be a vectorized operation.
What's the difference between the two graphs? Because one applying soft thresholding and the other isn't?
Yeah, I think this graph, this graph is corresponding to this optimization problem. Well, we have L1 norm that's in blue, and this is like a shifted quadratic function. This is like shifted quadratic function. It's a negative of this quadratic function. So I think it's different. I would suggest we look at this soft thresholding operator directly. Yeah, because this one is looking at the optimization problem itself. Okay. So yeah, maybe this figure is better. It's more intuitive to explain this sparsity and the soft thresholding idea. Yeah, honestly I don't see any difference between these two graphs. Yeah. But I think we can just look at this soft thresholding operator.
That makes sense.
Yeah, and you see the lambda that we put in the regularized lambda that we put here controls the threshold of this operator. Okay. So this is how we can control the level of sparsity that we want. It's also fits intuition, right? If you choose a bigger lambda, we are penalizing this L1 norm heavily, which means with a bigger lambda, we are filtering out more coordinates. So yeah, so this also is consistent with our intuition. Okay, so yeah, we will continue next time to talk about other advanced properties of this operator. Okay, see you guys. I will see you on Thursday.